Welcome. My name is Will Mars. I'm the founder and president of Endurica. I will be leading today's session. We are recording now, and we will be distributing recording to everybody who registered for the webinar. If you do have questions, we do plan to answer them at the end of the presentation. So feel free at any time to enter your questions in the chat, and we'll get to them at the end. The topic for today is building tire models and how we can make that easier using a tool called Coreform Cubit and a plugin for Coreform Cubit. We're joined today by Dr. Karl Merkley, who's an independent consultant who has a lot of experience with the tool. Let me say a few words about why all of this matters. I joined the tire industry in 1992 as a co-op student for Cooper Tire and Rubber here in Findlay, Ohio. But one of the very first jobs that they gave me as a co-op student was to take the cut sections of tires, and we had a special room lab up in the attic of the building, and we would lay out the cross sections on the desk, and we would hand draw the sections, taking careful note of all the different layers in the tire, laying out the cords, measuring all the gauges along the cross section of the tire. And we were doing that for a couple of reasons. Obviously, competitive analysis and checking the dimensions of the tires. But I was pretty soon involved in a research group at Cooper Tire. That's so after I did a rotation on my internship with the research group, and we used those dimensions to build, at the time it was kind of bleeding edge, finite element models of tires. Of course, in the years that have come since, finite element modeling has come a long way. But if you're going to build a finite element model, you have to start with geometry. And, we've got better tools for making geometry these days. But in my old past history, we spent a lot of time building in-house tools to build the tire geometry, and then more importantly, for modeling, to turn that into a finite element mesh. And that can be quite an involved process. Since I started Endurica in 2008, I've had the opportunity to see workflows in a lot of places. And we noticed getting good geometry and turning it into a decent mesh and having flexibility to operate on that mesh when you're trying to get a model to run, that can be a pretty big bottleneck for people. In fact, I put together this slide, which is just a very, let's say, high-level overview of the workflow that typical tire simulation goes through. And I've just tried to put some estimates, kind of went from my own experience, but I also asked the Copilot AI, and it gave me similar numbers to these. If you were to try and build up a model from scratch, just using the out-of-the-box tools that we have, you're probably looking at something like this. So measuring your cross-section properly and getting your geometry all laid out in a CAD program, you might be looking at 6 hours. Taking that geometry and then bringing it into a mesher and cleaning up the geometry and making all the definitions, you could be looking at a day there. Setting up boundary conditions and pre-processing, that's usually a smaller task. I've painted that as 2 hours here. The execute time, obviously this depends on how big your model is and what resources you have, but I think 4 hours might be a reasonable, typical thing. Of course, when you're doing these workflows, you hope that your model runs on the first try, but it's often the case that you get to the end of the run and maybe you don't have convergence, or maybe the run reveals something in the model that you kind of missed in setting the model up. And so it's pretty common to have to iterate. Now, if the iteration involves just a change to boundary conditions, that's usually pretty easy, but you still have to go through the solve phase. If the change involves something where you're going to have to tweak the geometry or the mesh, that can get more involved, because then there's a lot of this longer workflow that you need to come back and redo. So we want to make this box as small as we can so that when we do need to come back for those iterations, we can maximize our speed through this loop and hopefully get pretty soon to the post-process side of things where we can just focus on telling the story of our analysis. So the tools we're going to show you today are really going to focus on the geometry cleanup and meshing. And that's where kind of the juice is, I think, in the process to add value for people. Just for people who have joined us who maybe don't know Endurica, I've got one slide here. Endurica is focused on helping people to predict durability. So if you've got a rubber part, how long is it going to last? So obviously that includes tires, which is what we're going to focus on today, but we do a lot of other things as well, bushings, mounts, and so forth. We have a software tool set. Endurica CL is our flagship tool. We do materials testing. If you want to characterize your materials for finite element or fatigue analysis, if you want to bring these methods into your own test lab, we can set you up with testing instruments to test the fatigue properties of rubber. We can do projects and we do training. To date, we're used by more than half of the top 10 tire makers on the Rubber News list, and we're really proud of that. Also, the big news for us last year was Endurica became a reseller of Coreform Cubit. Coreform is another company, our partner company, that for a long time they've had this product Cubit on the market, which is used by several tire companies already. It is a powerful preprocessor that does hex-dominant meshing. It's really strong in its scripting powers, and that's what we're going to leverage today. Also, in the future, you'll probably hear another webinar from us on the topic of IGA, isogeometric analysis. So Coreform is very much at the forefront of bringing IGA tools for people who need those. So that's my introduction. I'm going to go ahead and stop talking here and hand off the microphone to Dr. Karl Merkley, who is an independent consultant. Prior to starting off on his own, he was the product manager and developer for Coreform Cubit for many years. He has 3 patents in mesh building technology, and he has a PhD from Brigham Young University. Take it away, Karl.
Thank you very much. So just a little bit more about me. I originally started working with the Cubit project in right around 2000. So Cubit's been under continual development at Sandia National Laboratory since around 1991. The first commercial version of what we call Coreform Cubit was released in 2004. I was part of the team that brought that to market. We helped put a front end, a GUI on it that still looks very much like what it looks like today. We made some decisions at that time that I think were actually some very good decisions. One of the decisions I'll take credit for in 2001 was that we looked at a number of different scripting languages, and we decided to use Python at that point in time. That's been a decision that's held up really pretty well.
That's
one thing
a
little bit prophetic. So one thing I will point out is that Cubit is a little more than just a meshing tool. It's not just a preprocessor, it's a meshing toolkit. It does a number of different things. The CAD import and cleanup, both hex and TEP meshing, lots of controls and tweaks coming out of Sandia for things that they needed. And we've got a very flexible licensing scheme as well. So let's go ahead and go to the next slide. So last year we had a customer come to us and they said, it's just taking us way too long to build a tire cross-section. Can you help us with this? And so we worked with them and they gave us rights for this tool after we were done. This is a script that's all in Python that goes through and imports the line drawings, defines material regions, applies boundary conditions. We mesh it and then we can export it. Our primary export target for this is Abaqus right now, but it was kind of a fun project to work on. And it just kind of emphasized for me the power of Cubit. You can download this tool that I'm going to demonstrate today from github.com, Coreform LLC. The QR code will take you there as well. Note that this is under an open source MIT license. The MIT license is one of the most open licenses there is. You can take this code, look at it because it's Python. You can modify it easily. When you bring that in, it pulls in a toolbar with these icons. Let's go ahead and look at the next slide. Importing this into Cubit, there's a toolbar that allows you to define these things. You do a right click, import it. Toolbars are nice because you can actually export these, share them with other people. So if you have a set of operations that you find yourself doing all the time, you can easily build a custom toolbar and share that around with people that are doing similar things. When you import this toolbar, there's, as I mentioned, all these different icons to do things like create surfaces, define material regions. You can blunt tangencies, areas where you've got sharp tangent intersections, add cut lines. This is just kind of a manual process. We'll go through some of that. in the end, mesh this, reflect it, add rebars, and build your model. So I think with that, I believe we're ready to just go ahead and start the demo. So let me go ahead and share my screen here. Okay, so this is that GitHub page where you can download this from, github.com Coreform LLC. And if we come down here, there's a tire cross-section tool. Here, there's some installation instructions, some usage instructions. You can get the code if you just download the zip file and walk through those installation instructions, run some batch files and bring it in. So once we're there, and here's Coreform Cubit. Just quickly, over here on the left side, we have some kind of your standard model tree stuff. You can see some properties over here. Over here on the right-hand side, we have a command panel. It's based on a mode, an entity, and an action. So I can say, oh, I want to do surfaces, and I want to modify my surfaces. I can pick different things out of there. Now, one of the things that I like to do, rather than running in with all these big icons, they take up a lot of space. I like to go ahead and come into my options and in the command panels, use the breadcrumbs. And instead of having all of those big manuals, now it comes up and gives me a breadcrumb up here that works kind of the same way, but it takes up less space. All right, let's come back to tools here, come into our custom toolbar editor. If I didn't have this already imported, I can right click on this, select the import file, select where I want it stored. Right now I've already got it in place, so I'm going to activate that. When I activate it, brings up my icons. Okay, so let's start with a simple model here. Let's import a recent. I'm bringing this in as a step file. This particular step file was created in AutoCAD, exported as AutoCAD lines, and it has the typical kind of problems that you'll see in AutoCAD files, for example. If we look right there, note that lines don't always match up. It's great if you're creating a blueprint because the printed lines overlap. You bring that into a CAD system and say, oh, I'm looking for closed models. Does not quite work. So the very first thing we have to do is take all these lines and turn those into surfaces that we can actually mesh. So I click on my geometry icon and it brings up a little GUI. This GUI panel, once again, is also created in Python. We use a tool set called PySide6 to create the GUI elements. It goes through and calculates what's my smallest curve length. I like, okay, that's relatively small for this model size. I'm going to take half that as my merge tolerance, run through some operations, and quickly turn that line model into a set of distinct regions that define different material regions. The next operation I'm going to do, I'm just going to proceed through this from left to right. I'll come in and specify, this is a one-ply model. Based on the fact that I know there is one ply and the fact that I have my model oriented in a specific orientation, just by firing some rays and making some assumptions there, I can derive some material groups. For example, I know the thing on the far right-hand side is the tread. Underneath that, I've got a rubber base. I can identify some belts. There's some regions here, like this little filler region, I can't really identify off the top. So these are unnamed. You may need to name those so you can define your material regions. There's our ply, for example. Now, down here at the bottom, one of the regions that I can't automatically identify is this region that I know is a chamfer. So I'll just right-click here, rename that chamfer in my toolbar. Now, when I go up right out of my element sets, I'll have an element set that's called chamfer. And in fact, later on when I'm doing rebar, I will identify that as a region that can contain rebar, and we'll mesh that appropriately. The next thing that I'll just do one quick example here. Notice I talked about areas of high tangency. This is an area that's, okay, no matter what I do, if I put a triangle in there, that's going to be a poor element quality because the tangencies here are so tight. That angle is highly acute. So one of the things that I have, a tool here, will come up and it's doing some processing first. There we go. I can select this vertex, select this surface, and say I want to back this off, let's say 5 units. Okay, you can see a blue line that got created across there. I'm going to take this tangent point and I'm going to back it off to this point. I'm going to blunt that tangency. So we split the curves, add different additional material on the sides, and then we blunt that tangency. When we go through and do another operation, it will actually join these curves together. So we'll get a triangle in here that is much less blunt than the original one. I could do these in other locations as well. For now, I'm just going to, for the sake of time, I'm just going to do that one. If I click on the triad there, it resumes, rescales things back to normal. If I ever do something like that, I can click on the triad, just get back to where I was. One of the other operations we probably want to do is introduce what we call cut lines. Now, cut line just takes me over here to the command panel and allows me to select different operations to introduce lines into the model that can help control skew. Typically, for example, companies may have some control over skew around the bead. So if I pick these two surfaces and then pick a start vertex here and pick an end curve over there, and I calculate the skew line between those two, I do that and I can split the surface so that elements here are going to be well formed as they go around this bead. This one's a little more problematic because if I import this, do this here, I could end up with some problems. We'll just do it anyway. We'll take these two curves. Now, one of the shortcuts here, instead of having to go back and forth and pick, if I hit a middle mouse button, it advances it to the next field. Hit the middle mouse button again. I can click that. Note that this has an underline on the A. If I do an Alt-A, that just executes it. Similarly, if I come and say, okay, let's cut from these two surfaces, notice that the focus was already in that top one, middle mouse button there, and a curve over here. All right, undo Alt-A. Okay, so we insert some things there. It's probably good to clean up this one as well, because we'll end up with high skew there if we don't. Let's preview that. Yep, that's right. So you can preview at any time to make sure that you've got the right things. Okay, and then we probably want to add in another couple of cut lines. Maybe we'll go ahead and pick up all of these belts and go through. Oh, my middle mouse button is acting up on me. We pick there, pick that curve, and apply. We cut those. Wow. So there's some cut lines. Now, one of the operations we will want to take care of, it's a Cubit kind of specific operation. It's called imprint and merge. It just ensures that all of the curves that are adjacent to each other know about the curves that are adjacent and ensures that we have a conformal mesh in the model. That operation's done. We can do what we call a composite curve. If you look at all of these vertices out here, if we hit that composite operation, it cleans up a lot of those small lines, removes extraneous vertices, and just kind of cleans some of that up. Now, one of the other places we might notice here is it failed to catch these because the angle is actually not continuous. So if I go into curve selection mode, select this curve and select this curve, I can also go ahead and manually just composite right here to get rid of those extraneous vertices. Tab key takes me to the next curve if I didn't get the right one to start with. And once again, composite. Okay, so we've gone through from creation geometry, definition of materials, blunting, adding cut lines, imprint, merge, and composite. We're up to the mesh step. So this is a quad dominant mesher. So it's going to put quadrilaterals everywhere we can. These surfaces are going to be specified as mapped surfaces. A mapped surface is on a, for example, in a rectangular region like this, we can put in a structured quadrilateral mesh, and that's what we call mapped. And the reason I want to do those is because I'm going to put rebars in these regions later, and I'm just going to go ahead and use the midline of the two quadrilaterals that I will insert there for rebar elements. Let's go ahead and do a mesh size of somewhere around 2. If I hit apply, it says, okay, this is an approximate element count, 1,800 elements or so. It will likely be higher than that because I'm just doing the area, saying what your mesh size was, and just throw a mesh on there. So there's a mesh. You notice, once again, I mentioned like here in the ply and in the chafer, we've got 2 elements thick through those regions. We've got pretty good elements coming off of this one. This one I may decide I wanted to change. Maybe I don't want a triangle right there. I could add another cut line here and force that to maybe give a little bit better mesh. So you want to take a look at these things and say, okay, is there anything I want to change? If I come down here and just do list, so I'm 2,200 faces there. I'm under 3,000 elements. That's a fairly reasonable size mesh for this. The next step, we're going to go ahead and define just a couple of simple boundary conditions. We can get others. If we select this vertex tip right there, add that selected vertex and create some boundary conditions. Now, if I look at, these are element sets that get created. If I draw, that represents the side where I'm going to put inflation pressures. So that just is denoted. This little circle is refresh and display. Also, we've got the tread that's defined. You could go ahead and add others. Those were the 2 that this customer said, okay, let's at least get these 2. Then let's go ahead and reflect this whole thing. And once again, refresh that. There's our model. Our element groups, again, are reflected. I was looking at the code, and there was some effort to go ahead and make some of these left and right, but does not look like that's in this version, which is where we're at. But once again, it is open source. You're free to change those as you want. There's our reflected model. Okay, we have these blocks that we defined, for example, that chafer region, the belts, the ply, that are automatically defined. Let's go ahead and create rebar in those regions. That added new material blocks down here as well. If we draw those, I got one extra one there. There we go. So you can see there's rebar elements. The other thing I can do with those rebar elements is I can actually visualize what, say, 19. Let's make the scale on that maybe a 3. I can visualize the 0 angle on that just to make sure that these are oriented in the correct direction. And I know from past experience that for an Abaqus analysis, that's the orientation that the rebar elements need to be so that Abaqus can process those correctly. At that point, really, once again, if I redraw my mesh here, we've gone through, there are a couple of other things that we can do. If you have an area where you want to move a specific node, you could. Also, there's a tool here that says, okay, zoom to bad triangles. All right, let's say that edge, I want to go ahead and just collapse this triangle, select the edge and apply. So that just in those areas where I've got high tangencies, I can go through and remove the bad triangles. Let's go to the one on the other side that's going to be similar. Select edge and apply. Go to the next bad triangle. There's one there. Select the edge and apply. This is a manual process. I could go through and automate it. My gut feeling on this one was, I think I want a person operating in the loop here so that we're not doing something really dumb. Okay. So our current bad triangle, we're up to a minimum scale Jacobian of 0.237. Let's go ahead and grab that one. And to the other side, let's see. We're now at 0.287. Maybe we'll go ahead and take this one as well. Notice that there are geometry lines that are being displayed here as well. So just be aware that that's okay. All right. That's up to like 0.294. That's pretty darn close to 0.3. I'm just going to stop there for now. Now, if I come over here and let's go back to our mesh and reset this thing up. I know that there's probably a couple of quadrilaterals that are bad too. But I can come and check my quality metrics. Let's select surface all, display my scale Jacobian. So in this model, my minimum scale Jacobian is 0.294. And most of these, pretty good. So from a quality side as a mesh guy, I'm pretty happy with that, frankly. We could, like I said, we could maybe push a few things to try to get that up above 0.3. But for today, I'm going to live with that. So the next step after this, we've gone through the entire toolbar. The next step would just be, let's go ahead and say export. Let's export this as an Abaqus file. That's the last thing I tested. Okay, we'll just go ahead and overwrite that model1.inp file that I have here, replace that. I'm going to write only the mesh file. So typically what most of our customers do is they have some boilerplate that has all of their materials and the way they want to run their analysis. And then we write the mesh-only file, and then they just import that into their boilerplate. We're going to go ahead and write this as, we can specify a 2D file, but this one is already there, I believe. So if we write that out, finish, there's our file. Now, if I put that in my junk directory, you can tell I'm old school because I use Vim or VI Model 1. There we go. So we have 4,109 lines of nodes. If I come down here and open that up, you'll notice that the elements are being written as axisymmetric Abaqus elements. You'll note down here for the rebars, they're written as axisymmetric bar elements. We have node sets and our element sets that get created, and all of our regions for our elements as well. Like there's our name for the rebar and the ply. If we open up one of these, open up, let's say, just nodes. Okay, there's our 2D nodes that have been written out. If we look at a set of elements, there's the element coordinates. So everything is there, ready to go with all your model, and that's ready to import into your boilerplate and run an Abaqus. And we got through that whole process in well under an hour.
Yeah, I think it's about, I took about 10 minutes of introduction, so I think you've been about half an hour.
So that was actually the goal for this company. They thought, okay, we would like to be able to do this in under an hour, certainly. Could I have added some more cut lines, done some more refinement here? Yeah, probably. I could spend a little bit of time trying to clean things up, but sometimes you just need to go run the analysis fast. So this is going to be, once again, on the order of 4,000 elements. And then look at your results and say, okay, is this good enough or not? We can look at the element quality before we do the analysis, but sometimes you have to look at the analysis and use your physics and the knowledge that you have in the domain to build a good finite element model. Okay.
Thank you, Karl. That was amazing. I'm going to just throw up one summary slide here. So hopefully this was interesting for people. We were really excited here at Endurica when we learned about this because we have been building lots of tire models from scratch here, and we just felt like this was a great time saver for us. It's open source, it's simple, it's efficient, it's powerful, it's flexible. And if you're interested, obviously you need to have Cubit. And if you don't have Cubit, then talk to us and we'll get you set up. So at this point, we're happy to take questions from folks. Just enter your questions in the chat. I do have one question here in the chat already. Is it possible to do these operations via a Python script?
Yes. Okay. If we come in to the download site, you'll notice that each one of these is individually a Python script. So if I look at, for example, tiregeometry.py, I come in here and here's my GUI stuff that I've added in. There's the fundamental create tire geometry method is just that. And it just runs Cubit commands and does other Python operations in Cubit. Could you go ahead potentially, somebody, for example, if they wanted, write an AI to take this, put in cut lines using AI tools? That's non-trivial, certainly, but somebody potentially could do that. Drive the whole thing as a Python script, perhaps. For me, there are still times when I think it's really good to have a human being in the loop, maybe with some AI assistance.
All right. Let's see. I see somebody has their hand raised. Noman Hassan.
Yes, I have a quick question. Yeah, so I saw that you were calling up some GUI windows to pass parameters to your capabilities. And if I heard correctly, you said you're using PySide. So just regarding that question, regarding that capability, is there any reason behind choosing PySide instead of PyQt? Because PyQt has pretty much the similar capabilities. So just wondering why you choose one over another.
PySide is actually the officially supported Qt. Once again, the Norwegians say cute. I've always thought it was a little bit too cute. So if I use the words Qt, our GUI itself uses Qt as the GUI implementation. PySide 6 is the officially supported version of the Python wrappers for Qt. PyQt5. We used that previously. And with this latest release, we decided, let's go with the officially supported version. The licensing on PySide 6 is a little less strict rather than being full GPL. The licensing is a little bit more lenient LGPL. Here, because we're distributing this as open source, there's no problems. So it was a combination of who's supporting it and licensing, why we went with PySide 6.
Thank you very much.
Let's see, we've got a bunch of questions here. So the next question is, can you comment on Cubit tools for tire tread meshing? And actually, the next couple questions are all around that. So what you showed us was all 2D. Can Cubit do 3D?
Cubit can do 3D. I have done 3D tire tread meshes. 3D tire tread meshes, Cubit handles the sipes very well, for example. The biggest issue I've found with trying to create treads is cleaning up the geometry and doing it in a way that you can create the minimal set of hexahedra. Everybody always wants coarse hexes, and the coarser the mesh, actually the harder it is to generate. Cubit uses a process of subdivision. If you're doing hex meshes, you've got to cut things up. Cubit's got some pretty good tools for cutting things up. I'd love to see those improved a little bit more for tires. I have done tire treads with Cubit. The other thing that I found that's a problem occasionally is someone will give me a piece of tire tread and just trying to determine, where do I cut this? How do I cut it up so I'm not creating small rectangular slivers? Triangles are death to a hex mesher. If I have to put triangles on the side of something, if I have a triangle on the side where I'm sweeping from top to bottom, I can't do that. So trying to determine where to take the cuts for symmetry and getting that all taken care of, that's one of the bigger obstacles I've seen in building tire meshes with Cubit, frankly, is those initial decisions of how to subdivide the treads.
Great. So for the tie constraint, is that something that the user would have to create separately, or does, like when you do a 3D tread, a lot of times you use a tie constraint to link the tread model to the carcass model? Is that something that Cubit would write out for us, or we need to kind of
so Cubit
do that
has,
ourselves?
You can define a contact region. You define those contact regions, and then you can create contact pairs and define those as tied constraints. And those will write out to Abaqus.
Brilliant. Here's another question. This model had small elements suitable for durability analysis. What about elements 2 to 3 times bigger for a footprint analysis? And also use plies with just one element thick. Is it more difficult to get a quality mesh in this case?
For this particular case, the way that I implemented rebar, and once again, this is just the way I implemented rebar. I implemented it as the plies being two elements thick so that I could find that midline easily. Yeah, could we go back and remesh this as a coarser mesh? Yes, getting high quality mesh as you go coarser becomes more difficult. But if you're doing a footprint mesh, you may not care about quality quite as much.
Yeah.
So
let's see. Next question. Have you started working on TetMesh 2?
Actually, Cubit has high quality TetMesh. It's the same TetMesher underneath the covers that actually Abaqus CAE uses. Sandia right now, who's our partner, is focused a lot on doing a specific element type of TET that they're finding really pretty good results with.
Are there licensing options for Cubit for academia?
Yes, there are. Cubit does have academic licenses. You'd probably need to contact Coreform, support@coreform.com directly. Kimberly, I think, is probably still on. She's the one who would handle that. We can get you.
And
we
absolutely
have. There's academic pricing, and you can get that through Coreform, but you can also get it through Indurica. You don't need Coreform to get academic pricing.
Okay, good. I'm not the marketing guy, so.
All right. Let's see here. Are there any methodologies to quickly convert a physical tire cross-section to a line model?
Ooh, to go back the other direction.
So basically take maybe a photo image of a tire cross-section and convert that into lines. And Karl, this kind of also gets to the question a little bit of, of what file formats you can read as input to set up your lines. I think you used the AutoCAD drawing file, but
Yeah, well, that's what it was actually output as a step file
okay.
from AutoCAD. So we can input step. If we do have additional licenses on CATIA, Pro-E, SolidWorks, anything else, Pro-E Creo these days, NX. So we have to pay a license fee to our supplier to give you those. We charge an additional fee, but it's just a straight pass-through cost. We don't charge any extra markup. What we pay is what we ask people to pay when they use those additional translators. As far as going from so if you're going from an image to, the question is about going from an image back to curves only.
Yeah, to the line model, to get the line model.
See, once again, I'm sure there are tools out there that can do that.
So I'll mention a tool that we've used. It's a free tool, actually. There's a tool called Graph Grabber. I'll tell you what, I'll look it up and find a link for everybody. No guarantees. Like I say, it's a free tool. We've used that in past. If we've got an image, you can just bring it. It's great for digitizing pretty much anything where you've got an image and you want to turn it into XY coordinates. So let's see here. For rebar element, your demo seemed to be for node sharing. How do you handle embedded rebar for Abaqus?
Right. These are all node shared. I currently, right now, I do not handle embedded. So you'd
have to make a different button for that, or right.
Somebody would have to tell me how Abaqus represents that and how I want to create those to start with.
Right. What about to make hex mesh of the tread with wavy sipes? So if you have a 3D sipe shape. So getting back to the general Cubit capabilities for meshing wavy sipes.
I have done wavy sipes before. They are a pain. So the biggest problem that I have seen there is separating. I have a wavy sipe and the bottom of the sipe has varying depths, right? So how do I separate? 3D Cubit does sweeping primarily. So we're going to start at the top and we're going to sweep down at the bottom. So we can put a hex or a quad mesh on one surface and sweep down, and we have to sweep from many surfaces down to one base layer, which is typically like the carcass layer, right? When we have these wavy sipes, the meshing, if they're all going down to the same layer, it's actually not a problem. If they have different depths at the bottom of the sipe, then you have to find ways to go ahead and cut those up and decompose that in a way that you can define that many to one kind of mesh. And that's...
let me make an additional comment on this particular topic. So, Coreform Cubit is a tool that's available right now. I think I mentioned at the beginning that there's currently another tool under development called Coreform IGA. We gave a talk that kind of foreshadowed this at last year's Tire Society meeting. But one of the core value propositions of Coreform IGA is the capacity to deal. It's a different method for dealing. It's a different method that doesn't require the same kind of finite element discretization, and its perfect use case is for complex tread geometry.
Absolutely.
That's not the topic of this webinar, but we currently have a project with Core. We've been partnering with Coreform to try and help develop this for the tire market. And you can expect that hopefully later this year, we'll have another webinar and be able to show more about that. But the tire geometry certainly has cases when you start getting into complex sipes and weird lettering that start to go beyond what you'll ever be able to do easily with the traditional methods. So that's where we see the future headed with IGA.
With IGA, you can bring in your CAD model and just go.
Yeah, well, we just keep getting questions here. Groups are created in the half model. After being reflected, would the two groups for the same tire component be merged automatically?
Yes. And I said, as I mentioned, I looked at the code last night and realized at some point in time, somebody had asked me to look at left and right, but I didn't. But if we look at the body ply here, for example, you can see the body ply group goes left and right all the way around. So after reflection, the groups are in the same group again.
Yep. Another question, can Cubit create effective tire meshes for other FEA solvers besides Abaqus?
I do have people that have used LS-DYNA. For this particular tool, if you wanted to go to LS-DYNA, you'd probably have to go edit the deck and specify the element types directly. You'd probably have to change that in the deck. But other than the element types, LS-DYNA would be correct, I think. What else do we have? Yeah, there is an ANSYS exporter. We go out to a general tool called Exodus, which is a National Labs formatter. So if you have any number of open source tools, will read the Exodus format.
I think we've covered all of the questions, and I've just got two other thoughts to share. One is, don't miss our next webinar. In 2 weeks, we are going to be doing another webinar from a really sort of different direction. So talk to your compounder friends, the people doing the materials development, and we're going to talk about using simulation in the service of materials development. We're going to have another guest join the webinar, Dr. Louis Tunnicliffe, who's the R&D director for Burla Carbon. They make carbon black that goes into rubber. And he's going to talk about using simulation in materials development. So that's going to be pretty exciting. We're going to talk about a service that Endurica has called Events, where we use finite element modeling to show materials developers how material properties relate to product performance. So don't miss that. The other thing I just want to mention briefly is our upcoming community conference. We did the last one here in Findlay, Ohio, in the United States. We're going to be doing the next one in Luxembourg in Europe. So if you're in the neighborhood, we'd love to have you join us. We've got a pretty exciting lineup of presenters and sponsors. There's going to be more coming. These are just the ones who've committed so far. But we're hoping to have a really nice cross-section of people who make systems, OEMs, people who make rubber parts or tires, people who make raw materials. It's going to be a full spectrum experience. Dimensions of durability will be the theme. And I think it's going to be a really great group to be with. So we're really excited about that. And so I will go ahead and sign off here. Thank you for joining us, and get durability right.